Okay, hello. My name is Cameron and welcome back to my video series on the MIT OpenCourseWare Computer Graphics 837 course. So in the previous video I completed assignment 0 and showed you how to get started with assignment 0 and also how to do it. And today we're going to be looking at assignment 1, curves and surfaces. So this one I'd say is far more difficult than assignment 0. I definitely got stuck on it for a little while and took a lot of thinking in order to get it to work. With that said, the only new thing I wanted to share with you that was helpful for me is that there is a YouTube tutorial series, or sorry, not a YouTube tutorial series, but the actual lectures for this course are also posted. And it looks like Justin Solomon has been posting the video lectures for this course on his YouTube channel. And so here's fall 2020, and this is actually one of the better lectures because you have the slides full screen, because I also looked at his video lecture from fall 2018, and I could not really see the slides, but that you'll see. Yeah, so I'll link to this playlist will be in the video description below. With that said, let's go ahead and jump right in. Let's see here. So I have the solution on my second screen here, and to start out I tried to get the starter files, just the regular zip file, to work. This contains just the CPP files, the header file. However, with my system I was not able to get it to work. I was trying to use it with Windows Subsystem for Linux. I was trying to use this thing just like I did in the previous video. I figured that doing it this way will give you like the most amount of compatibility for whatever system you're running. Unfortunately, I couldn't get the dependencies to resolve. I kind of just like was fixing one thing after another, and I just couldn't get it to run. So I downloaded the Microsoft Visual Studio 2010 zip file, and I'm going to go ahead and download this again to start from scratch and show you how to build it step by step. So let's head over to my folder here. Should have an MIT folder. Yep, here we go. Assignment 1. Let's call it YT for YouTube, and we'll save it in here. Cool. So if you don't have Visual Studio Community, it's free. Visual Studio Community. There it is, and it's free. Cool. Go ahead and just head over to this website. I can put the link in the description, but I'm assuming if you're here, you probably already have this installed. So let's not waste anybody's time, and we'll just power forward. So we'll close that. Let's view this file we downloaded, and we're going to extract. Okay. So I believe if you just click on the SLN, it's going to open the solution. And on my other screen, I have the splash screen for Visual Studio opening. And it's starting up. And let's see if I can move this. Oh, I cannot move this. So I'm going to have to temporarily switch screen displays. I hope I do this right. Okay. So the first thing that popped up for me, because I'm not on the 2010, I'm on the 2019, is this retargeting projects. I believe when I first saw this, all I did was leave everything on default. So for me, that was 10.0 and latest installed version, upgrade to version 1.42. I just clicked OK. And then it did its thing. And then I was in. So let's make sure that worked. I am going to move this to my other screen. So give me 1 second here. Okay, we're good now. So if you click on the Solution Explorer, we should be able to see everything that we have here, including all these source files, header files, everything. And the nice thing here is this vec math. I ended up heavily using this VecMath to get this assignment done. So VecMath is pretty important. Luckily, the provided files come with VecMath, so that helps a lot. Before we go any further, let's open up the handout and see what they're asking us to do. So in this assignment, we're doing curves and surfaces. And so for this case, the curves is the Bezier curve and the B-spline. And then there's actually something interesting that I got working, which is converting control points for a B-spline in terms of a Bezier curve, which I also have timestamps for where you can go learn more about that in the lecture videos from the actual course. And then the surfaces is actually just using like, the profile or like a silhouette, and then just rotating or revolving the profile around 360 around the y-axis and creating a surface. So these wine glasses are actually images created from completing this assignment. And what they did was they had like just a silhouette of a wine glass, and then you sweep it around and boom, there you go. Pretty cool. So let's go down here to getting started. One thing that was useful for me is I did still download the starter code, and I was able to run the final solution of what we're supposed to get, but I won't open that up right now. We don't really need that right now. Okay, so what do we got to do? Get started. So solution 1.0 is included, or A1 solution is included in the starter code. You don't need to change anything other than its execution permissions, and try running core. So to do that, maybe we will open it up. You'll go ahead and download the starter code, and then you are going to use whatever. I like to use Linux to run this, so if you have VirtualBox or something, you can do that. I'm going to be making a tutorial series on how to set up Windows subsystem for Linux like I have here, but that's a video for another time. So what I'm going to do is pop this guy in, start up my X server, and then I need to navigate to this folder, which I already have shortcutted. There we go, ls clear. So this should be the folder that you download. And we have A1 solution. So if you run /A1 solution SWP, so that's that SWP directory. Inside there should be wineglass.swp. Oh, we need sudo. So let's go home, sudo, run it. Type in my password. There we go. Very nice. So if you push the S key, you can see all of the vertices for this object. Push S key again, it turns off the surface. You're left with the control points in yellow. And then if you push P, you can turn off the control points and see just the curve. So this is B-spline drawn here, cubic B-spline. And if you push C, you can highlight the normals and the binormals and the tangents. And then if you push C again, you can turn it off. And push P, bring it on. Push S to see the cup. Very cool. And then, yeah, so that's all there is to it for running the solution, the completed solution. But how do we actually make it, right? So we'll keep this open for now, and we're going to switch back over to Visual Studio. Well, okay, so we can run the getting started to see what everything looks like. I like to work with the core, and I'll show you how you can change that and get started with that. So this is good to read. We're going to skip right past it and jump right in. So curve is 45% of your grade, yada, yada, yada. Keep going down, starter code. Yep. Cool, implementing curves. So I would recommend reading through this, and if you don't really get it, it's kind of fuzzy, don't worry about it. This is the kind of thing where you have to just keep going over it and convince yourself that all of this stuff works, like I had to do, because my first read through of this, it didn't make perfect sense. As a matter of fact, I stopped to write about here saying, okay, I don't really know what's going on, and that is when I came across this lecture series. So really, your focus should be on lectures 2 and 3. It doesn't matter what semester. I recommend the fall of 2020, and that's what I'm going to link below, but you can also switch over to this channel and go to the different playlists and see the different semesters that were recorded. There's 2018, there's many different semesters. So if you want to hear it explained in different ways, maybe students will ask different questions during different semesters, definitely give that a try. But let's assume you are ready to start programming. Let's get started. So the way I'm going to do this is I'm going to implement the Bezier curve first, and then we're going to implement the B-splines, and then we're going to talk about the surface of revolution. So I have this totally 100% done, and I'm going to be going off of what I did and then kind of explaining to you my thought process on a new one. So hopefully this isn't too disorganized. Let's just go ahead and get started. So this is where we are, and then this is what I made. So everything here is pretty good. I believe if we just hit play right now, it is going to try and display the wine glass, and it's not going to work. Okay, so this is all you get when you hit play. You get this terminal. The terminal says all of the control points for the B-spline and the steps, and then it just says returning empty curve because nothing's implemented yet. If we push P, we can turn on and off that. C, there's no curve yet, and S, there's nothing. Okay, cool. So the first thing I noticed is in the Solution Explorer, you have the curve.cpp. And in here, this is where we're going to be doing our first step, which is defining this function, implementing Bezier curve. So to do, you should implement this function so that it returns a curve. Cool. So I kind of looked through this, and it just says like it's eval Bezier curve has been called. Get the control points. How many are there? It counts out the control points and prints that out. Returns the steps and returns an empty curve, and then returns an empty curve. Nothing's implemented. B-spline we're going to do last. Well, not last, but we're going to do after Bezier curve because, like I said before, I'm going to be actually doing the conversion that is required as suggested here. You implement the function by changing the basis from B-spline to Bezier curve. And then eval circle, this was actually, my core, like what I started with. So like basically, this shows how you can make a curve, and then you can fill out this curve with time steps t. So this was pretty helpful. So what I did was actually I copied this, and this is evaluating a circle. So we copied it, and then we just put it right in on the Bezier curve. So we're going to comment out returning empty curve. And this is kind of what we're going to be working with. So radius is not defined. Where do we get the radius? Radius is an input. So we can change that to be something defined like a radius of 2. Cool. So you can kind of read through this and convince yourself. Basically, t is going to be from 0 to 2 pi, and then you're just evaluating cosine t and sine t. And this is going into a vector 3, and then we're scaling that, and v is going to be your vertices or your points, and then t is going to be the tangent, n is going to be the normal, and b is going to be the binormal. So all of these things are required, and they're all explained in this document. Also, interestingly enough, the binormal is, I believe, somewhere in here, it says it's simply going to be defined as unit 1 in the positive z direction. Okay, a fixed binormal, selecting a fixed binormal. Okay. So we'll come back to that. In this situation, it's set to, So the binormal is dependent on the previous binormal. So that's what I did in my code. Sorry, I was just trying to remember. Yeah, so in this case, binormal is always facing up for this particular circle. So we can run it, and we're going to see a curve drawn. There we go. We don't have the curve yet. How do we get that curve? Oh, so we didn't get the curve because we're not evaluating a Bezier curve for that wine glass. That wine glass is drawn with a B-spline. So how do we change it to one of the other example files? Well, the best one to work with, I think, is actually that core. So to get in there, all you have to do is click the little drop down up here and click one debug properties, and then switch to debug, and this is where you can change the swap file or SWP file that you are going to be running. So I super recommend working with core because you're going to be drawing each type of curve. No surfaces yet. We're going to be doing surfaces last. So now if we hit run, we still don't have any circles. Where's the circles at? All right, I'm going to pause the recording. Okay, sorry. It took me a second to figure it out. I just didn't want to leave the recording running while I figured it out. But the problem was I never updated the return value to be R, so it's still returning an empty curve. So that is important. So now you'll notice that your Bezier curve, evaluate Bezier curve, is creating a curve called R, and then down here in the return statement, it's returning R. Whereas before it was returning curve like this. This returns an empty curve, literally. So I think if we hit play now, we got to make sure I close this terminal here, because then when I hit debug, it'll make a new one. Okay, now we're talking. So this is what comes out. So this is okay, you know, like we have successfully drawn our first curve, you know, into our environment here. It's just the wrong kind of curve. So this is just kind of giving you an idea of how to get started with drawing a curve. And the step of copy and pasting into this method isn't necessary. It's just where I started out. Yeah, okay, so how do we develop this into doing the curve we want to do? So for that, I think what I'd like to do now is refer to what I did on my own time over the past couple of weeks and start remembering things. So the first thing that I saw, and this is coming straight out of the lecture, is right below returning empty curve. The first thing we want to do, so I'm going to put a to do, is think about counting number of, what did I say? Bezier subcurves to chain together. And then my reference for you, I actually have the timestamp. If you go to lecture 3, fall 2020, at timestamp 00:32:48. So go 32 minutes in and 48 seconds, and you are going to see the professor actually talk about this problem and why you might need that. But I can also show you right now what we're talking about here is when you get a set of control points, you need to figure out how many control points there are. So ignore the circle. I'm going to turn the circle off. This guy is 4 control points. That's going to be for a Bezier curve right there. And then also this guy, 1, 2, 3, 4, that's 4 control points. So that's pretty easy to think about is, okay, there's just 4 control points. I can work with that. So we can't just hard code 4 control points every single time because there's no guarantee that every single time there will be 4 control points. For example, if we looked at the solution doing the wine glass, you'll notice if I turn off the surface, turn off the curve, there's far more than 4 control points. We got to work with having like a piecewise Bezier curve and segmenting them together. So in this case, for the Bezier curve, the way the Bezier curve is defined, and I'm going to switch back over to this one to explain this. Basically, the Bezier curve, it is going to always go through touching. So the curve that's going to be drawn is always going to start at the first control point and then do its thing and then touch the last control point. So starting at 0, t is equal to 0, it's going to be touching the control point, and then when t reaches its final value, t equals 1, it's going to be touching the final control point, which is different from B-splines. But so basically, another thing to think about is in the lecture, I don't have the timestamp for this one, but if you watch those lectures, there's one thing he talks about, which is the de Castel algorithm. I am probably saying that name wrong, but I can do a quick Google search. De Castel algorithm. De Castro, no. I believe it's in here. If I search for de cast, no? I'm probably spelling it wrong. Okay, I'm going to pause the recording and find it. Okay, we are back, and I found it. So this is it's this one right here, de Castel's algorithm, and basically it's in the slides here. This is the slides from, or the lecture notes from the actual website, but he also talks about it in the video lecture. But the idea here is you can, if you want to do 1/2, you can split these two control points in half, and then split these two control points in half, and then split these two control points in half, and then draw line segments between those control points. Then you can split these two control points in half and these two control points in half and get these 2 points and draw another line segment. If you split it in half, then this is going to be the curve evaluated at whatever value you decided to split in half. So you can do thirds, so third, third, third. You can do 2/3, so 2/3, 2/3, 2/3, and then you'll get the 2/3 point on the curve. So this is a way of estimating any point on the curve using this method. But the thing that I learned from this example is that every Bezier curve is always defined by 4 control points. Yeah. So what that means for us is we want to draw our Bezier curves 4 control points at a time. Okay? So how do we count the number of control points, or sorry, count the number of subcurves to chain together if we're taking 4 control points at a time? So how I decided to solve this was I defined a counter, so subcurve count is equal to 0. And then if the p size is exactly equal to 4, then we're going to do sub curve count is equal to 4. Okay, and then 4, so now we're going to iterate through unsigned I equal to 1, I is less than p dot size. So basically we're just using a for loop to count 4 at a time. Minus 4, I plus plus. And then subcurve plus equals 4. Okay. Very good. Ooh, let me try that again. So I actually made a mistake. I was looking at my B-spline code. So this is going to be a little bit different. Okay, so we actually want to start from 0, and we're going to go all the way to the end. And the way I did this, instead of using modulus, I decided to use an if statement because I felt like it. p count is equal to 0. So p count is point count, and it's going to start at 0, and then p count is going to go up plus plus, and then once p count hits 4, we're going to set p count equal to 1. And then subcurve plus plus. And then get rid of this guy. Okay, there we go. Okay. I'm going to go on pause for a second. Okay, I'm back. I just wanted to get some water real quick and draw this quick diagram to basically convince yourself of this algorithm for counting the control points. So we have subcurve count starting at 0 and p count, so control point count starting at 0. And then for I equal to 0 and it's less than p size, so each element in p go to the next one, and p count is going to go up. And then when p count reaches 4, it's going to go back to 1, and subcurve count will increment. So what I have here is basically what's going on, and there's many different ways of programming this. I'm not saying my way is the best way. I just kind of got it to work and moved on. But basically we have 0, 1, 2, 3, and so that is a total of 4 control points. So p count is going to go back to 1 instead of going back to 0, because 3 is counted and it's also simultaneously 0. So 0 is already counted, so p count is going to be 1. Hopefully that makes sense. It made sense to me and it works. And so you're also going to say, okay, that's 1 subcurve, and then we're on to counting the next subcurve. Cool, cool. Okay, so we'll minimize that. Where do we go from here, right? Let me take a look at what I did next. So next up, we can pre-allocate our curve. Instead of steps plus 1, it's going to be the number of subcurves times the steps. So because basically what we want is I'm going to use a new color here. We want to do a nice cubic curve flowing through here, and then we're going to evaluate it in steps of t. So t is going to be these steps coming through here. So basically, however many subcurves you have, that is what you're going to be multiplying the steps by, and that's going to be your total curves. And so this curve is basically, I think I can peek definition here. Curve is just a curve point, a vector of curve points, and a curve point is, well, I don't need to peek that, I can close this. The curve point basically has the v, the t, the n, and the b. The binormal, the normal, the tangent, and the vertice or vertex. Okay. So we're going to modify this to now be subcurve count times the steps plus 1. Cool. Now, the next thing we're going to need is the spline matrix. Spline matrix. So basically the way this is going to work is we're going to get matrix of 4 control points, and then we're going to get matrix of monomial basis, and then we're going to calculate position. So that is going to be the control points, so geometry matrix times the basis times the monomial basis. And then this is going to give you the position. So it's going to be like a vector vector 3f. It's going to give you your x, y, and z. And then we need to calculate the tangent, which that is going to be the geometry points times b prime, or the derivative, times the monomial basis. That's going to be equal to vector 3f. And this is going to be the tangent. Then we also need to get the normal, so calculate normal. That one is going to be the cross product of the binormal and the tangent we just calculated. And then it needs to be normalized. And then we need to calculate binormal. Calculate binormal. And that one is going to be the tangent cross product with the normal. Yeah. Oh, one note is this is going to be previous binormal. So whatever the previous binormal is, that's going to be the new normal. And also this is going to be normalized. And then we need to save binormal as previous binormal. So hopefully it'll make sense as we start to code this out. So let's see, this spline matrix, right? This one is given to you in the lecture, and because we're using vecmath, you can just pop it into a matrix for f. I'm going to call this one Matt Bernstein. Okay. And then it's going to be 1.0f, negative 3.0f, 6.0f, and negative 1.0f. And then we have to add in some more. It's going to be 0.0f, 3.0f, negative 6.0f, and 3.0f. Then we have, how come that's red? Oh, it's because we're not done typing. 0.0f, 0.0f, 3.0f, and negative 3.0f. Then lastly, we have 0.0f, 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 and 3.0f. Okay. Oops, I did not get this one right. It's 1. I was looking at a different matrix. That's why I was like, that doesn't seem right. I thought 1 went here. Okay, so we define this now because it's never going to change. It's a constant. This Bernstein matrix is straight from the slides. So let's keep going, keep chugging along here. Next up, let's get the, this is going to be the Spline Matrix. Actually, let's not do that. Well, yeah, we have to. The Spline Matrix derivative. So before I start defining it, I can define the monomial basis matrix. And this is also from the lecture videos. The monomial basis is actually going to be a vector for f. Vector for f. And what do we have here? We have 1, and then t, and then t squared, and then t cubed. So t isn't defined yet, so it's going to highlight it as red. But basically, I just put this here so we can talk about taking the derivative of this guy. So I'm going to copy this, copy, and paste. And then the derivative of 1 is 0, so this guy becomes a 0. And then the derivative of t becomes 1, so this guy becomes just -3 still, it doesn't change. The derivative of t squared, am I doing this right? Hold on. Okay, so basically the way this works is I put the, so the original monomial basis is 1t squared t cubed, and I've taken the derivative here, so became 0, 1, 2t, and 3t. And if you go through and multiply, this whole column becomes 0, 0, 0, 0. 0 times 1 is 0, 0 times 0, 0 times 0, 0 times 0. And then -3 times 1, it's -3. Actually, this is a 4 by 1. Oh, this should be the transpose. This should be 1 by 4. Anyways, let me keep going here. 1 times 3 is 3, and 1 times 0, 0, 0. And then 2 times 3 is going to be 6. 2 times -6 is -12, and 2 times 3 is 6, and this one is going to be 0. And then 3 times -1 is going to be -3. 3 times 3 is 9. 3 times -3 is -9. And 3 times 1 is 3. So this is our derivative matrix. And let me just double check that this is right. I'm also going to switch back over to here. There we go. Close these guys. Pull this one back up. So this is what I was saying. Let me see what I did last time. 0, -3, 6, -3, good. Yep, this is what I used. Okay, cool. I just had to make sure, do a quick sanity check that I'm not messing anything up now that I'm recording. So this is going to be -3, 6, -3, too many negatives. We can tab this guy in. And this is going to be positive, good, good, good. -12 here. This is going to be 6. That's going to be a -9. This is going to be a 9. And this is going to be a 3. Okay. Cool. So we're going to save that monomial basis for later. The only other thing we need to do is we need to have a vector 3f. This is going to be for our binormal. And then we need a vector 3f for our previous binormal. So vector 3f previous binormal. Cool, cool. And let's make sure we give this a unique name. So I'm going to call this matrix Bernstein prime. Okay. And then now the last thing that I'm thinking is that we're going to need, why is this color not changing? That's a little bit weird. We're going to need an int k index, and I'll explain that for later, but it'll come up, So for unsigned I is equal to 0. I is less than p dot size minus 3. And then this is going to be, are we in the right spot still? Yes, we are. This is going to be plus equal 3. Right? Because we need that last one to be the first one of the next one. And we already kind of talked about that with that diagram we drew earlier. Okay, so this is going to be a little bit of a fancy, I use the Tertiary Operator. That's what it's called, right? As long as nobody's looking. So basically, if the condition is I is equal to 0, then we need to generate a binorm to use for this very first one. It's going to be arbitrary because there is no previous binorm to go off of. So we can just say 0.0 f, 0.0 f, 1.0 f. And then if we're not, if we're not on I is equal to 0, then we're going to use the previous binorm, which we'll set later. Cool. Now this is where we're going to be entering into our main loop, right? So I is going to be iterating through our control points, and yeah, we are good to go. Let me check something real quick. I'm going to pause the recording. Okay, I just wanted to make sure before I say something, I wanted to make sure it was right, so I just tested it out on my working solution. And basically, we're ready to get our matrix of control points before we enter into the T steps. So this is actually going to get cut and then pasted in here. Okay. But before we do that, we're ready for our geometry matrix. This is going to be a matrix for F, and then I called mine control points, and then it's going to be PI, position 0, then we have PI. I'm going to pause it and type this whole thing out to save on video time. Okay, there we go. So we just got a matrix of control points. This column here is going to be the very first control point. This is going to be the next one to it. This column is going to be the next one to it. This column is going to be the next one after that. This one's going to be the next one after that. And then we have 0, 0, 0, 0. And so that is our control points matrix. Now, before I had this defined inside of the step loop, but you don't need to be recalculating this matrix every single time. So it's better to calculate it once and then step through it. So I made that change in my original code, and this is what I'm going to do for you guys as well. So everything here is looking pretty good except a couple of things. We don't need pi, so we can just do float I. Another problem is we can't use I here because we already used I there, so we need to rename this guy to be J. So let's go through here, J, and J, and J. And then we'll just split the comment to say step. Okay. And then this is where we're going to use T. So we're finding T. So basically T is going to be J out of steps. And you can think about this one, but basically it's going to give you a floating point number that is going to be exactly a step through out of 1. And we can make our monomial basis here now. Vector for F, mono base. And it's always going to be 1 T. Oh, wait, didn't we already do it? Didn't we already do this? Yep, we did. Control X, Control V. There we go. Looking good. Cool. And now we're ready to start filling out some information. Can you believe it? Okay, so here's the tricky part. And this might take a little bit of thinking about, but you can't index through this curve. Where? You can't index through R, this curve R, using I. Because there's going to be, you know, steps times subcurve. You can maybe do some sort of equation. No, I don't think so. I think it's easier just to make another variable k and then just access R using k. I think this is like the easiest to think about. So you're just going to use k, and use k. Then after we're done, we're going to do k plus plus. Okay, so that's how we're going to step through the curve R. I feel like this is the most straightforward way to do it. Okay, so the result here is going to be a vector 3. We don't need that. And we're not using cosine here, so don't use cosine. It's going to be control points times the matrix Bernstein times the monomial basis at position 0. Then next up, it's not going to be sine. It's just going to be this guy again. At position 1. And then after that, it's not going to be 0. It's going to be this guy again. And that's going to be at position 2. Boom. Just like that. Now there seems to be... What's the matter here? I'm going to pause it for a second. Oh, just a small typo on my part. It took me too long to find that. I think I'm like, once again, getting fatigued from all of this back-to-back talking. Okay, so that's all there is to it. We can change that comment to say calculate V. Cool. Now we'll move on to the tangent. So the tangent is not going to be minus sine t and cosine t. Instead, it's going to be basically the same thing we have here, except for one thing. And that is we're going to be using matrix Bernstein prime. Let me see, prime. And then copy and paste. Cool. Also, don't forget, we can just simply add a dot normalized, and that VecMath library will handle the normalization. I don't even have to code that. It just works, which is awesome. Cool. Now the normal is a little bit different. We're going to be doing the cross product of the whatever the binormal is. Right? What did we say? Calculate normal. So this is actually going to be vector 3f, and we're going to access a function in here called cross. And we're going to take the binormal. Oh, it's capital B, huh? Binorm. Norm? There it is. And rk dot t. So whatever we just calculated up here, that value. We're going to take the cross product. And we got to normalize it. Dot normalized. Open and close parentheses. Boom. Nearly there. Next up, we have the binorm. So the binorm for this guy is going to be the previous, or the tangent that was just now calculated, and the normal. And now that I think about it, well, no, I think that would complicate things. Cool. And then lastly, we got to keep track. So we want to track the binormal. So previous binorm is going to be equal to rk dot b. Excellent. And we've done it. Believe it or not, we've done it. Let's see if it works. I hope this works. I'm going to be a little bit sad if it doesn't work first try. What's that guy? Something strange happened. So, what did I do wrong? All right, I'm gonna stop the recording and debug what I did wrong. Interesting. That's pretty close. Okay, I found the mistake, and it is I copied the Bernstein matrix incorrectly. So this should actually be a 3. And 3, -6. Good. 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 Okay, let's try that again. Yes, there we go. That's what I'm talking about. So that is some Bezier curves. Looking good. Cool. Let's get the B-splines going. So for the B-splines, this one I did something tricky. So we can delete these comments, and we have all of the code to make a Bezier curve. Good, good. Here we are on the B-spline. So in the B-spline, we need to transform the basis. And this is something that was explained, where was it? So we still need to count. Oh, I don't think we need to count anymore. Let me pause the recording just to make sure. Okay, just made sure. Basically, we don't need to count the number of segments for evaluate B-spline because of the way that I've defined it instead. So to start off, we are going to go ahead and make a empty curve. So we're going to do curve, and we're still going to call it R, curve R. And we're not going to say anything about its size. It's just going to be totally empty because R is a vector, so we can just do pushback. And what I'm thinking is we can get a single curve point and then push it onto the curve, which worked kind of better for me. So I just need to check a couple more things. Okay, so I don't need that variable either. Okay, so let's go ahead and get started with writing the B-spline matrix, and I explain what we're going to do. So B-spline matrix, this guy is going to be a matrix for F, and we'll call it mat B spline. Okay, and this one is a little bit different. So we can look at it at, if we go to, I'm going to pause the recording. Okay, so on lecture 3, 43 minutes and 57 seconds, there is this, the Bezier matrix and then the B-spline matrix. So this is 1/6, and then there's the matrix. So basically what we're going to do is we're going to type in all these values and also divide by 6. Each element gets divided by 6. So we're going to type that out. And I'm actually going to pause the recording and just copy and paste it. Okay, so I went ahead and copied and pasted in all of these predefined matrices. You can see here I put some timestamps. Let me make the font just a little bit bigger. Is there a zoom in? I think that helped a little bit. We could probably do a little bit more. I put some timestamps up here. Should have done that earlier in the video. Sorry, guys. Okay, timestamps up here to learn more about the matrix. These are just some interesting notes that I wanted to take for myself. You can go check out these timestamps if you're interested. So I brought back the matrix Bernstein, or the Bernstein matrix, and then I also created the inverse of the Bernstein matrix. And basically what we're going to do is we're going to let's open up the preview of the window so we can explain what's happening. So basically these other two guys, those are our B-splines. And so this is a good example because it's exactly the same control points as this Bezier curve. So the B-spline is going to be something that's like a tiny little sliver right here. The B-spline does not go in, it does not touch the first control point, does not touch the last control point. You can make it touch if you keep adding more control points on top of each other. But in this case, these are just all one control point. So basically what we want to do is make the B-spline, but what we can do is we can transform these control points to be control points for a Bezier curve that's going to draw our B-spline. So if that's a little bit mind-bending and a little bit hard to follow, because I know I said that really quick, the professor likes to say, I don't know if you parsed that, but if you parse that, basically what I'm saying is we're going to do a transform on these control points to put the B-spline in terms of a Bezier curve, and then use our Bezier curve code to draw that B-spline. So basically the control points are going to be tiny because on the Bezier curve, the curve will touch the starting control point and the final control point. So how do we do that? Well, it is explained in the lecture, and I can also do a poor job of explaining it, but basically let me fast forward to when he has all of the notes up here. So basically you have your geometry matrix, and then your basis matrix, and then your monomial basis matrix. And then over here, if you have a different kind of basis, you know that multiplying by the inverse and then multiplying that by basis is going to give you the identity. So if you can also say like this, these two things are equivalent because identity matrix is just the identity matrix and it doesn't do any operations. So if we take our geometry and take our basis and then also do the inverse of the Bezier basis, then when we give it to the Bezier basis, it's going to multiply by this and basically cancel out the Bezier basis, make it one, the identity, and that leaves just our basis. So we're using the same code, but we're getting our basis put in there. If that's hard to follow, watch this lecture and think about it, but it works. I got it to work, and it makes sense after you see it working. So let me go ahead and switch back over to the coding. So basically the whole point of what we're trying to get to is we want to be able to say eval Bezier inside of our code. So we can't do it yet, we have to work up to it, but we want to do that. Okay. Yeah, so I should add that you need this singular variable because I guess you need, like, this function requires it, and sometimes you can give a matrix that cannot find the inverse, so it needs to be singular. Small notes. Okay, cool. K is equal to 0. We need this guy. You'll see why later. I'm doing that same trick as before of having a second iterator that I'm using for custom purposes. Unsigned I is equal to 0. I is less than p dot size minus 3, and then I plus plus. Another thing I want to point out for the B-spline is we're doing something a little bit different here. Don't save. So in the B-spline case, let me move over here so I can use the pen, and let me switch to this one. Okay, so for the B-spline, what we're going to be doing is we're going to have some control points. And then the B-spline, we're going to take 4 of these control points and send it off to the Bezier. And then we're going to take the next 4 and send it off. Then we're going to take the next 4, and you see how they're overlapping. We're going to send it off. Then we're going to take the next 4, and we're going to send it off to the Bezier and evaluate it as a Bezier curve. So that's the plan. Let's program it. Okay, so we have our for loop good to go. Okay. And this is the time to get our control points. Now, lucky for us, we already coded that, so I'm just going to scroll up to the top here and get this control point matrix and scroll back down and use it again. We need our control points. And then this is where we're going to make a new matrix. Matrix 4F. And we're going to call it, I like to call it G bar, and G bar comes from the lecture video. He called it G bar right there. Go full screen. G bar. Okay. So we're making G bar, and G bar is going to be the control points times the matrix B-spline. So this is our B-spline basis. And then the matrix Bernstein inverse. Good, good. Now, next thing I did was I made a vector of vector 3s. And I called it new P. So this is the transformed control points that we're going to feed to our Bezier, evaluate Bezier curve. So basically the idea is we're going to give this guy new P, and we're going to give this guy steps, right? And we're sending it off. Okay, so but now we need to build the new P. And for this one, I kind of got a little bit lazy because it was giving me a hard time. This is just the way I decided to do it. Vector 4F G bar dot get column 0, and then temp 0 is going to be equal to column position 0. I guess I could have gotten the sub matrix now that I think about it. Yeah, I wrote this line of code when I was still kind of learning how to use the VecMath library. I'm still not totally up to speed on everything that it can do. But this was just like, I didn't want to learn it, and so I did it this way. And then I kind of learned a few things along the way. So I probably should update this code, but I have not updated this code. So this is a little bit messy. Okay, so basically we're making a vector 3 temp, that's a control point, and then we're going to push it onto new P, which is a set of control points. And we're getting the G bar column, which is a vector 4F, and we're just getting the first 3 elements off of that column, which is the XYZ of the control point. And we're pushing it onto new P. And so we need to do this a few more times. This time don't reinitialize column. And this time we're taking get column 1. I guess I could have put this in a loop too. I don't know. Two. And 3. Okay, and then I also made a new curve, and I called this one sub R. So this is like a tiny segment or a tiny subcurve. That's the tiny Bezier step in this B-spline. And then sub R is going to catch whatever's coming out of Bezier. Cool. So hopefully that makes sense. So what we've just done is we've taken a tiny 4 pieces and sent it out to the Bezier, and then we've taken the curve that comes out. Cool. Now we need to take all the curve points and put it on the real curve. So this one, I was having some weird glitches happening. So I basically decided to do it this way, where I just take them one curve point at a time. Actually, do I still need this? Unclear if this is even necessary. Yeah, this is necessary. Okay, so we're going to loop through here for unsigned J is less than sub R dot size. So now we're going to go through and take all of these points and put them into our curve. J plus plus J. And then for some reason, I'm starting with 1. And yeah, I don't need this last curve point. That one can go away. This one can shift tab. Okay, there we go. And then we have a curve point. PT. And then PT dot V is going to be equal to sub R position J dot V. And I think you can see what we're doing here. But basically, we're going to get each component T, N, N, and we got B and B. And then we can simply say R dot pushback to push the curve point PT onto our vector that we're going to output. We're going to increment K. Oh, we don't even need K, do we? I don't even think we need this. I'm going to pause and make sure we don't need this. Okay, yes, we do not need this, because we're going to be loading up the curve points dynamically instead of trying to pre-allocate our curve vector. And we don't need last curve. We got rid of that too. So there you go. Now, so I think we can run it, but there's a small bug I had to fix. So let's go ahead and run this and see what we get. Nice. Boom. B-splines and Bezier curves. So we can check if this is right by opening this guy up and running the core.swp. Type in that password. And we can compare. And we can see that they're basically identical. I can't really see anything wrong here. There we go. Very cool. So we're not quite done yet. I think if we fire up the wine glass. The wine glass is the one I like to look at the most. So let's switch this over to wine glass. Wine glass, go. Run it. So here's the wine glass. That looks pretty good. And we can compare with the solution. Well, the solution has the surface. We can turn that off. Turn off the control points. They look identical. They look pretty good. Nice work. Cool. All right. So there is a bug I'm going to have to fix. We're going to have to come back and modify the B-spline curve after implementing surfaces. But let's go ahead and implement the surfaces. So to get the surfaces working, it was pretty complicated. I'm going to pause it for a second. Okay, so I was not able to get the surfaces working. Basically, I found this GitHub, Andrew Mo 2014, and he had a solution for the surfaces. And so I basically just tried running this code, right? So let's take a look here. And I will link this GitHub in the description below. But if we open up our Solution Explorer, go to Surfaces, and go down to Make Surface of Revolution, you can comment this guy out and paste in code from there. Just double check I got this one right. Make surface, yep. Let's see what that looks like. Oh, I should have changed it to the wine glass. Oh wait, I think I did. Oh wait, this is still open. And boom, simple as that. We have the surfaces. And the same thing worked for Generalized Cylinder. Generalized Cylinder. I once again used the code from this GitHub, which I'll link below. And I did read through it, but I didn't spend as much time. I was just happy that it worked and that I could finally get this video put out. But feel free to study this code and take a look at it. Paste. Save. Okay, so for the generalized cylinder, this is where there's a bug that we have to fix in the code that I have before. So if we do the example of weird, okay, and run it, there's a small bug, and I'll show you how I fix that bug, and then we're going to wrap this video up. Okay, so there's a crack. There's a crack in the weird model, and that's not supposed to be there. So I fixed it by going back to my curve, the B-spline curve, and basically, I guess there was one segment that my loop missed, and so what I did was I added add missing segment, and basically it's just this guy right here. So this is control point 0, 1, 2, 3. And I went back through and just ran through my whole algorithm again and pushed that on to the curve. So same process. Oh yeah, I named it something different, didn't I? Matrix B-spline. Matrix B-splines, a capital S this time. Okay, save it. Same process. We're making G-bar. We're getting a new P. Then we're loading up temp, pushing those back, and then we're making a subcurve calling evaluate Bezier curve. We don't need last curve point. We're never iterating on j is equal to 0. We're loading up the curve points, and we're pushing it back. So, and that again was for the missing segment 0, 1, 2, 3, and then 0, 1, 2, 3. So I don't know why that one's missing, but now if we run it, we should be safe. And boom, now we got it. Cool. Well, I hope this video was helpful for you to get started. We have just covered everything for getting this assignment to work, except for the surfaces. That wasn't my code, but everything else is good to go. And I will again link this GitHub in the description below, so you can read through that code and study this, and hopefully this was helpful. There's lots of extra credit things to do here, so hopefully this is enough to let you work on these extra credit project ideas. We have the generalized cylinders, so you can study this. We have the code from that. Not my code again, but it's code nonetheless that we can study and learn from. I learned a ton for doing this project. I was so stumped for the longest time on how to even get started on this. One thing that I learned that was a huge takeaway for me is this whole VecMath library, and basically just using the just keep like when you're using linear algebra formulas, just keep them as matrices and do matrix multiplication. Like for some reason I was trying to turn these into like equations rather than keeping them, like I was trying to get rid of the matrices and program equations and evaluate equations, and it just seems so brilliant to work with these matrices instead. That made so much more sense once that finally clicked for me. If you have any questions, let me know. Hopefully this was helpful. One last time we can kind of look at some of the stuff that we made here. So here is that weirder. Is this weirder? Weird. This is weird. Let's look at some more. What about that wine glass? The wine glass should still work. So we can get that wine glass. There's the wine glass. That looks great, man. Cool. Yeah, that's pretty much everything. Thank you so much for watching. Let me know if you have any questions, and stay tuned and subscribe for more videos like this. Thank you. Bye-bye.